I don't think with this smaller room we really need the screen. I'm just going to record what I do on the board, and then we'll put that up there. Okay. And so let me talk about what the course. So this course is Advanced Thermodynamics, and the advanced part is really meant to just be deeper, not necessarily harder. Okay, so it's not like you have to say, oh, it's advanced, therefore it's got to be 10 times harder. Okay, it's more deeper in certain areas, and so we're going to go deeper in computational chemistry. We're going to go deeper into solvents because that's my specialty, and then we'll go deeper into liquid vapor equilibrium. So what's happening when things evaporate? Okay. And then thermodynamics. Well, thermo is energy, heat, and work. Talk about that. And then dynamics is change. So not everything will be at equilibrium. We'll actually have non-equilibrium systems like distillation. And so when we're talking about distillation, we have change going on. It's a dynamic. So that when we talk about dynamics versus statics, even equilibrium systems are dynamic. They're changing, but they don't appear to be changing. Okay, so if you do a composition analysis, you get the same compositions of products and reactants. If they're at equilibrium, you'll get a consistent answer, but those products and reactants are changing into each other at the same rate. So there's dynamics going on. You just don't see it. It appears to be static. Okay. Now, some of the very basic things that I'd like to cover involve, whenever you're dealing with heat and work, the different units. So what kind of units do you guys know of to deal with heat and work? So let's just sort of survey all the units we've ever come across in terms of heat and work and force and pressure and so on. Joules. Yeah, so joules. So let's start with joule. That's good. What are the fundamental pieces of a joule? So inside a joule, what is a joule? How would you define it with the fundamental constants?
SI units?
Yeah, SI units. What are the SI units of a joule?
What is it, like kilograms squared over like meters?
Yeah, so let's work this out. So a joule is a unit of energy or also work, right? And so work is a force, working against a force, for a certain distance. And so if I lift you up 1 meter, okay, you weigh a certain kilogram value. And what's pulling you down? Gravity, which has the units of acceleration, which would be meters per second squared. And so we can work this out. We're lifting a mass a certain distance against gravity, which has the units of acceleration. So kilogram meters squared per second squared. So that's work. That's energy.
It's like a Newton meter.
Mm-hmm. So that this idea of force equals mass times acceleration, that's a Newton. So Newton is mass and acceleration. So acceleration is meters per second squared. There's the mass. And so then we could have a joule is equal to a Newton times a meter. So you're working against a certain force for 1 meter, you've done a joule of work, if that force is 1 kilogram meters per second squared. Now all of these things are using seconds, meters, and kilograms as the basic units. Okay, and so we have a name for that. Do you know the name for that? Have you this unit system?
Are they SI units?
They're SI units, but there's two versions of SI units. This is the most common one. And it's metric, so we're using the metric system, SI units, but this is one version of SI units. There's two, actually, versions of SI units. And so this one uses M, K, and S. So that's the MKS system. Meter, kilogram, second system. Okay. And this is a joule. Has anybody ever thought about the word ergonomics? What is that? What is that about?
Yeah, efficiency.
We think of efficiency, but it's really not efficiency, it's energy. It's how you use the energy of your body, you know, how it's being taken care of, if you will. Okay. Ergonomic design is focusing on the energy. Like if your mouse is way up here on your desk, you're expending a lot of energy to use your mouse. You're leaning way forward and holding your head up, which is a very heavy organ, you know. And so the erg is also a unit of energy. Yeah, an erg, E-R-G. So ergonomics is the nomics of ergs, the economy or the house of energy. So erg, E-R-G, is also an energy unit. I don't know if it has a little single letter designation, like Joule has a J. I don't know what it would be for erg, so I'm just going to leave it spelled out. But we know that energy is a force times a distance. Okay, and we know it ends up with these things. We have that mass, we have a distance scale, and a second scale, or time scale. And so what do you think might be another option for mass? Instead of kilograms, we might just use grams. Okay. So grams, and instead of meters, we might use smaller units, like a centimeter. And there is no other unit for time. So that's an erg, a gram centimeter squared per second squared. And that's ergonomics. But also you'll see with delta G, when we're talking about delta G and spontaneity, you'll see the term, instead of exothermic, therm is enthalpy. What would you say if delta G was negative? Instead of exothermic, which would be negative delta H, it's exergonic. And so that word erg shows up, and that's why I like to talk about it early on, so that you know, oh yeah, erg is a unit of energy. It's just a different unit system. Now that doesn't mean that you have to use these units when talking about delta G. It's just vocabulary. Exergonic and endergonic mean it's giving out free energy or taking in free energy. That it's delta G is negative or positive. Just like delta H, negative or positive, is exothermic or endothermic. Okay. And then you could probably say exentropic or endentropic for delta S. Okay, but I haven't really heard that very much. I just say positive entropy or negative entropy change. But exergonic, endergonic, I've heard. You'll hear it too. And so I just wanted to alert you that erg is a unit of energy. And now, what kind of system would this be? Remember, M was for meter, so here we have a C, so it's a CGS. So that's the CGS system. Still metric, still SI, although some purists would argue with you. And so that's a little bit on different energy units. Now we also have calories, kcalories. We have nutritional calories, which are kcalories, so it's confusing. Use a capital C for a nutritional calorie, which is a kilo little c cal. And so there's just no way to know and remember all of those things. And so just find you a good reference that has conversions for all of those. There's also British thermal units, BTUs. So like a joule, you also have a BTU equals some number of BTU. Always put two T's in British. I don't know if that's right or not. I never remember what that is. I just always have to look up the conversions.
I didn't know it had to do with joules more than it had to do with, it was like the heat required to change the gram of water, or kilogram of water, 1 unit.
That's a calorie.
But that's, I think that's also a BTU, I thought.
Well, it'll be so many calories, but it's an energy measurement, and then BTUs per hour would be power,
Right.
and watts is power. So that's one thing we haven't talked about. This is energy. Let's look at power.
Let's stay away from BTU.
So a joule per second is a watt. And so when you get your electric bill and you see that you're charged for kilowatt hours, so a kWh is a kilowatt hour. It's really multiplied. It's a kilowatt times an hour. So you use so many kilowatts times how many hours you've got. And notice that a watt is a joule per second or energy per time unit. And then you multiply by time. So when you buy electricity from the electric plant, you're buying joules. You're buying a measurable amount of energy. And so it's coming into your house at a certain rate, which is the kilowatt rate, a certain speed, joules per second or joules per hour, and then you multiply that by how many hours you used, and you're actually buying joules. Yeah. And if you have a generator or a solar cell or whatever, and you're selling it back, you're selling joules back to the power company. There's another one we're not going to get into, but there's really strange energy units. Like tons of cooling capacity, so they'll have certain benchmarks that they'll use as units of energy. So you could use for your air conditioning, they might say you need a 10-ton unit, okay? And you've got to pull the thread to see how they're coming up with that, okay? But a lot of times the energy units that are used are very confusing. Like, what is a 10-ton unit? And it has something to do with how many tons of ice or whatever it can convert. So you could eventually pull the thread and get to how many joules that thing can pull out per second. So that's very interesting. Okay. Any other units that people can think of while we're on the topic? EV, electron volts. Very good. So
The voltage required to make an electron, what was it?
I don't know. What do you think?
I remember reading about it.
Yeah. So an electron volt.
To make one electron go from. It's not like to jump from optical, it's something else.
It's to move through a potential of 1 volt.
Oh.
Yeah, I think it's 1 electron accelerated with 1 volt of electromotive force. That's the energy that it has. Yeah, and so then you can convert that. I've got that conversion here. Let's see. Somewhere. I don't have the numbers, but essentially it's 1 volt. I mean, this EV looks like it might be a unit, but this is the charge on an electron, and this is 1 volt. Okay. And a volt is an electromotive force. It's the force being put on that electron. And so this tells us that energy, okay, another unit of energy is coulombs times volts. So a coulomb times a volt is electrical energy. Ohm's law, volt is current times resistance. And so you could have coulombs times current times resistance. So and so that'll give you joules. These will all give you joules. You can, some conversion will give you joules.
There's also Hartree's.
Yeah, Hartree's, which again would be atomic units. We'll see those. Hartree. It's like 2,000 something, like 2,600 joules per mole. Putting in per mole, you can take any unit, anything, you can multiply by Avogadro's number and get it per mole. So that's totally fair. If I wanted to know how many joules a Hartree was, I could just divide this by Avogadro's number to get rid of the per mole, and that would tell me how many tiny little joules is in one Hartree. And so I guess that leads us to another principle that I'd like to emphasize. This is going way back to freshman chemistry. So any equality can become a conversion factor. I want to emphasize this because this really gives you the freedom to think through a problem. You may not do it the most direct way, okay? But if you can work with the units, you can figure out probably 80% of the problems, just working with units. Because if I know that 1 inch is defined as 2.54 centimeters, then I can use that as a conversion factor. If I have 3 inches, then I know I need to get rid of inches and get into centimeters. And so this is an equality. This actually means defined as. When I show 3 bars, that means it's defined as. That means that there's an infinite number of significant figures. So you could think of it as 2.54 with an infinite number of zeros. This is not going to limit the precision of your experiment.
7.62.
Okay, thank you.
Thanks for it.
But what I want to see though is you want to see the units. I want to go ahead and put these in here so that you can see that any equality shown here can become a conversion factor. And you can write them upside down or right side up. There is no upside down or right side up. Okay? And why is that? Well, if you think about it, if this is equal to that, then you're just multiplying by 1. Right? It's an identity operation. The only thing you're doing is you're just changing the units and how you speak about that, the identity of that number. This number, 3 inches, is the same entity as 7.64 centimeters. You're just using a different description, using centimeters, and so you have a different number to go with it. Okay. Very important concept. Okay, let's change gears, and now let's try to do a survey of all the constants that we know. Okay, we might not remember the numbers, but Boltzmann's constant, yay.
1.381. 10 to the 100. Times 10.
This will be the most important one for us early on, okay? Typically given the constant K, 1.38 times 10 to the negative 25, 23, 0.38 to the negative 23. Yeah, so just like Avogadro's number, but with a negative. So 223 joules per Kelvin. And so I'd like to move away from you just seeing that constant and kind of memorizing its value or just not thinking about it. But look at those units. What do you see? What do you see in those units? Okay? You see a joule, and K is Kelvin, okay? Say again? Yeah, what depends on temperature? The joules, right? Yeah, this is a conversion factor. If you have a change in 5 Kelvin, that's a change in 5 times this number, joules. So this is telling you how many joules are moving around by a change in temperature. That's pretty cool. This is a thing that connects temperature to energy. That's very, very important. And so we'll use that a lot. Okay. Some other constants. Planck's constant. If you really want an interesting, well, I think it was interesting. This morning's lecture to the quantum class, I did a history of quantum mechanics and quantum thinking. And it's been revised over the years as I'm trying to write this book. And so this was the first chapter in the book to talk about where quantum thinking came from. And Planck's constant, he called the elementary quantum of action. So it was the slope of the photoelectric effect in how you change the frequency of light hitting a metal and the kinetic energy of the electron increased. So you move the frequency up, the kinetic energy of the electron increased, and the slope of that line was Planck's constant. Okay. And so that's one of the places where it was confirmed and then very accurately measured. 6.626 times 10 to the negative 34 joules times seconds. So this is a weird one because it's not joules per second. A lot of times we have a per in our units, but this is not. So don't mess that up. It's a common mistake. When you're looking at a problem and you just can't figure out where it went wrong with the units, that might have been where it went wrong. Okay, it's not joules per second. That would be a watt. Okay. So this is Planck's constant. This has to do with some of the very smallest changes that we can measure in nature. If you think about that. And so this also could be defining with time some of the smallest units of time. Now that's like a current controversy. Is time quantized? And they talk about some of the smallest units of time being a Planck time. So a 10 to the minus 34 second. Okay, so they're getting down into the beginnings of the universe as they study the origins of the universe, and they're getting down to sort of what happened in the first amounts of Planck time. And so when you hear that term, we're talking with this unit, you can see it's something on the order of 10 to the minus 34 seconds. Very, very small time. Okay. Other constants. We talked about Avogadro's number. And also it's good for me to write this because now you'll see what I think of whenever I'm talking about the Avogadro's number. I use capital N with a subscript capital A. So whenever you see that in my notes or in any of my PowerPoints and so on, when you see that, that's Avogadro's number. Yeah, and this is such a weird thing. It's like per mole. And this thing on top is just things. We don't ever say things. We do this with frequency too. What's the unit for frequency? Per second. What per second? Per second. Cycles per second. But we don't ever say cycles. So we leave the things off. I don't know why that is. It just always has been. Sort of leaves it generic. It's, Avogadro's number of cars or whatever would probably fill the universe. But, Avogadro's number of carbon atoms is 12 grams. I mean, that's a small amount of carbon, but if you think about how many atoms there are, 10 to the 23rd. I was talking about the photomultiplier tube in the last lecture about how you could multiply it up to 1 billion electrons, and that sounds like a lot of electrons. It's not really. 1 billion is only 10 to the 9th. This is more than twice that. More 2 times that. Yeah, it's just incredible. More 1 billion times that.
Say it.
Say again?
The gas
Yes, okay, so let's think about this one. So one of the first things that Boltzmann studied was gases. And he was dealing with large numbers of particles and so on, and so he was always using his constant and Avogadro's number together in studying these gases. And so he would take his constant, K, and multiply by Avogadro's number in A. So let's do that.
It's like 8 point something.
And so
Well, those two are
you put those out, the 10 to the 23s cancel out. You have joules per mole Kelvin. That sounds familiar. We've used that number a lot. And that is the gas constant.
I don't know it was K on A.
Yeah, so that's R. We've given that a term R. It's the gas constant. And if you just convert the units, you end up with the other version of the gas constant in liters atmospheres per mole Kelvin. Okay. And so, if you wanted to do that, liters atmospheres, so let's think about this joule on top. A joule is equal to a Newton times a meter, right? We established that. But let's think about in terms of pressure. Do you know what a
Force over an area.
yeah, force over an area. So pressure, we didn't really talk about those, but a pressure unit like a Pascal is a Newton per meter squared. Okay, I'm not getting that. Yeah, I'm getting that. So that's a Pascal. That's a pressure unit. Okay, can we figure out how a joule can be a Pascal? So let's put this in as a conversion factor, because this is an equality. So this will be some practice. Okay, I want, instead of a joule on top here, I want to have some pressure units. Okay, so let's write this out. So we're going to say joule per mole Kelvin, all right? And I want to get rid of the joule, and I want to put in this newtons per square meter somehow. And so let's go ahead and write out what a joule is. So a joule is a kilogram a meter squared per second squared. Now notice I had said a joule on bottom. Everybody follow this? Make sure everybody's got it. So a joule is on bottom, and then on top is a kilogram meter squared per second squared. Now it looks like the second square is on bottom, and it is. It came down when I said per. Okay, so that is that equality of a joule is equal to a kilogram meter squared per second squared. Okay, so that's that equality right there, and the joules are gone. Okay, that's nice. Okay, and then a Newton. Let's go ahead and write a Newton on top. Okay, is a kilogram meter per second squared. Okay, mass times acceleration. This is going to be crazy ugly, but that's okay. We'll have some fun. All right. So I've used Newton is equal to a kilogram meter per second squared. Now, lots of things are canceling. The second squareds are gone. One of the meters is gone. The kilograms are gone. Okay. And so then I want, so joule is a Newton meter, so that's nice. Okay. Now I want to get this unit of pascals in there. And I want it on top. Okay. So I'm going to put this Pascal on top. and that is equal to a Newton per meter cubed, or meter squared, sorry, meter squared. And so the newtons are gone, and now I have pascals, meters cubed. Okay, that's a volume. That's kind of nice. Okay, and I could leave it like that because I've got pressure and volume, but I really want to work in atmospheres. And so 1 atmosphere is defined as 101,325 pascals. That's a definition. So that's our definition of atmosphere, is 101,325 pascals.
That's how worded people who define these.
Say that again?
So I like how worded people define these numbers.
Yeah. We're running out of space. We've got to finish up. Drop this down in here.
We're going to do meters cubed to liter.
Yeah, let's go meters cubed to liters.
Yeah.
Okay. Do you remember how many of those there are?
Cube.
Thank you.
Let's see. So we'll have to do. Meters cubed with this one. Meters cubed to liters.
Is it 1,000 liters?
1 kiloliter, yeah.
I think it's 1,000 liters, right? Because a decimeter cubed is 1 liter.
Is the 1 liter.
Okay.
So 10 times.
10 times 10 times 10 would give us 1,000. Yeah, so 1,000.
It sounds good.
Okay, and so then we've got down here, we've got meters cubed is 1,000 liters.
Until proven otherwise.
Yeah. So what have we done? We've taken the joule and the gas constant, and we've gotten rid of the meters cubed and
Pascals.
all of the things like that, and we've gotten rid of pascals, and we're in units that we like to use. We like to use liters for gases, and we like to use atmospheres for gases. And so this essentially is, again, 8.31 joules per mole Kelvin times 1,000 divided by 101,000, okay? You could really just put a decimal place there and get rid of that number, okay? And so it's divided by 101.325 is the net result. So what is 8.31 divided by 100? Basically, it's 0.082.
Yeah.
06, yeah. So that's equal to 0.08206 liters atmospheres per mole Kelvin. So they're the same constant, they're just different units. Now that's the longest way to get there. But it's a good example of hacking your way through it, brute force. And you just keep going until you get what you want. You wanted liters and atmospheres, and you just keep going. That's that higher level skill of figuring it out, working your way through it, you know, application. And so this would be the application skill and the analysis skill. You're analyzing where you are, and you're thinking about where you want to go, and you just keep going. And most of the time, like I said, 80% of the problems you can figure out just with the units. You may have to look some things up. You may have to look up what an atmosphere is with respect to a Pascal. So let's say you're on an exam, just to be practical, and you do this, but you don't know that number. It doesn't matter. You put an X there, or a box, or a question mark, and you keep going. And in the end, you say, okay, I can't compute this number without that number, but I got the units I want. And that's great. If I saw you do that and you didn't know this number, big deal. Because what have you shown me? You've shown me you know how to think through the things, and you just missed one tiny little piece of it. Okay, so that's great. If I saw that and you kept working even past something that you didn't know, but you kept going, that's golden. Okay, because as soon as you have access to the internet or something, what are you going to do? You're going to go look up that number and finish. You know, and so it's not that you don't know what you're doing. You've shown me that you know what you're doing. And so that's the skill I really want. So you may think this morning was just review, but it's not. It's an example of how to think your way through the problems using the units. Just basic working with units is probably the #1 skill that you need. That's the first 2 or 3 levels. That's the remembering, lots of remembering. Okay, understanding, the using equalities, and then application and analysis. And then eventually evaluation. Does this make sense? You know, and so we really don't have any questions to think about in respect to that, whether this makes sense. But I think that's great. So we'll see you Monday. Things are going well. I saw people getting on the quiz